Okay, so let's look at a problem that's similar to the last one. Only this time, the angled launch is happening from some height that we're not going to neglect. So imagine, you have a ramp on your desk, and you roll a marble down the ramp, and the ramp leaves at some angle 30 degrees. So theta is equal to 30 degrees above the horizontal with some initial velocity here of 10 meters per second. So we're going really, really quick. But it's also raised off the ground initially. So this makes the problem slightly more challenging because there was an assumption that we made earlier that the change in the y direction would be 0. Okay, we made this assumption, delta y equals 0. This is no longer true, okay, because it's starting from some height here, right, and it's going down to some height here. Sorry, I've got the ink to shape button pressed. It makes the writing easier, but I don't know, sometimes it makes things weird. Okay, so it's going down some amount. I'm trying to shape it again. Let's see if we can get this fixed. All right, it's going, let's make sure to turn that off. Yep. It's going down by some height, delta y. Let's assume a delta y here equal to 1.5 meters. Okay, and it's launched at an angle of 30 degrees. So it's gonna end up going down 1.5 meters. All right. The questions that we have is how far will it travel away from the desk, right? So it's traveling off in this direction. How far is it going to go from the desk? So it's the same approach. We need to figure out t. How long will it take for this thing to hit the ground? And then apply that to the x component of its initial velocity, right? So this is, you got it when you're working a problem like this, you got to think about it one dimension at a time. So first, we've got to think about the y dimension. How long will it take for it to hit the ground? And to do that, we need v in the y direction. And then we're going to apply that time to v in the x direction to figure out how far it will go. Now, this is going to be trickier. This situation is going to be trickier because you're going to have to solve a quadratic later, and you'll see that. But the first thing, we need to break this initial velocity of 10 meters per second into its components. So our initial velocity vector is some 30 degrees roughly. Let me put ink to shape back on. Let's see how this works. I think it works actually well for shapes. Who would have figured, right? So it's some 30 degrees above, and this is an okay 30, 60, 90 triangle. It's not great, but this is our V naught. I didn't actually turn ink to shape on. That's okay. This is our V naught, 10 meters per second, and we can find v in the y direction here and v in the x direction just like we did. And these are initials, so I should have a little circle here. Okay. We can find that just the same way we did using SOHCAHTOA, right? So if I want v naught in the y direction, you just set up your right triangle here. Here's theta, right? Opposite over hypotenuse, right? So sine of 30 degrees, right, equals opposite over hypotenuse, or v naught y over v naught. Put the vector hats on there. And then we can solve for v naught y. V naught times sine of 30 degrees equals v naught y. And I'm not going to ask you to remember sine of 30. Well, actually, don't quote me on that. AP might ask you to do that. But you are going to use it so often that you will remember sine of 30. So sine of 30 is 1/2. Okay? So this simply becomes v naught times 0.5 equals v naught y. Okay? or 10 meters per second times 0.5 equals v naught y, which is 5 meters per second in the y direction. So we can find the time it will take for this thing to hit the ground. So we need to use a kinematic equation that has time in it, but also one that has displacement in it, or distance, because this thing is going to travel to the ground. So the equation we need is y after some amount of time is equal to y initial plus v naught in the y direction times t plus 1/2, and it's at squared, but we know a on Earth is, and this thing is in free fall, is going to be g squared. Okay, so we're immediately back to where we were in the other video, only this time this delta y is an actual value. Okay, did I ever assume how? Yeah, we said delta y is going to be 1.5. So y of t minus y naught, right, is delta y, or 1.5 meters equals v naught y times t plus 1/2 g t squared. Okay, and we have values we can plug in for this, but what you're going to notice is that this is a harder problem to solve, because when this is 0, right, when that is 0, this gets easier because you can factor a t out, and then things are easier because 0 makes the math a lot easier. Here, if you factor a t out, things are not any better. So you're better off just using the quadratic formula to find t. All right, now the quadratic formula will give you two answers. One of them is going to be a fictitious answer because it's going to say negative time. And if you think about that, all the quadratic formula is telling you here is it's telling you the values of t where this thing has gone down to 1.5. So if we draw this thing's motion, right, it's going to hit the ground somewhere out here. But if you were to somehow go backwards in time, it would have hit the ground back here. And that's where our fictitious answer comes into play. So you'll have to solve the quadratic for this. And to do that, you want everything on the same side and set it equal to 0. And I'll go ahead and plug the numbers in for this. So this is 1.5, right? And this is your C term in quadratic. Let me make sure I'm doing that right. Yeah, I think that's the C term. And it's negative because we moved it over. This is all equal to 0 plus v naught y, which is 5 meters per second. And that's times our time plus 1/2 gt squared. G is a number. It's 10 meters per second, right? 10 meters per second squared is g. And conveniently, we have a 1/2 in front of it, so that's going to be 5 meters per second squared, and this is t squared, right? So we can solve the quadratic here. Now, some things to keep in mind about negative signs, all right? If you get confused with the negative sign, which I may have very well done in this problem, what will happen is you're going to get a negative under a square root. Okay, if that happens, you know that you've made a mistake with a sign somewhere, and you simply need to go back and fix your assumptions. So if we end up getting a negative under a square root, that's incorrect in this problem, okay? So one of the assumptions we may have made incorrectly here is I said that the change in y was 1.5, right? The change in y probably should have been negative 1.5 for consistency's sake, right? It's going down by 1.5. So if the change in y was negative 1.5, over here, when we brought it over, this should have been positive 1.5. So I'm already seeing a place where even I just made a sign error, right? And g is 10 meters per second, but that's negative. So this should be negative, right? Now, conveniently, the way I made the error, it wouldn't have actually made a difference because I changed the sign twice. It looks like I'm running out of time here, so we might have to continue this in the next video. But just know that we're going to solve this thing with the quadratic equation in the next video, okay? And if you get an imaginary answer, you've made a sign error, and you need to go back and sort it out. All right, I'll see you in the next one.